Hello class, this is CSE-5250, section 60, week 6, fall 2023. So for this week, we have quite a few things to go through. And maybe you're starting to look at pthreads on your own, but maybe you don't, maybe you're in a situation where you're unable to do that because say you're on a Windows computer and you don't have access to pthreads. Well, I have a solution for that. So if you'd like to follow along with the demo programs for pthreads, but you're on a Windows machine and you don't have pthreads installed, follow through these instructions and you can then use PowerShell to compile and then run your C programs that use pthreads. These instructions were adapted from a scalar.com page that explains how you get the that explains how you get the C compiler on Windows. It's a Linux it's basically it's gonna be the same thing as we would have on a Linux machine because the textbook was made for use with a Linux machine. If you have Windows, good luck, but also it's not so much good luck getting it to work, but we have instructions to get it to work. So I posted these instructions on Canvas, but I've also adapted them into a PowerPoint format with pictures on for nearly every step of the process. So once again, these are instructions for setting up the GCC compiler on a Windows machine so you can compile your C programs the same way you would on a Linux machine. I'll show you what you do if you were to use a Visual Studio instead. But anyway, we begin by downloading MinGW. You can find it at the SourceForge link here, for example. Avoid all the ads that misdirect you by clicking somewhere else. RuneScape 4 and 3, Murder on the Border. Play now. Play your way. Old school RuneScape. No, don't click those. We want the big green download link that has the little SourceForge logo on it. That's the one we want. That's step 1. Step 2 is we download that folder. No, we download that in the downloads folder. We will have downloaded the installer. Run that. You'll see a window pop up. Click install. When you're going through the installer, you might see this pop up. You might see this window pop up here. MinGW Installation Manager Setup Tool. Specify installation preferences. Leave all of these settings unchanged. But keep note of where you're installing MinGW. Write down this path. We'll need that later. Continue with the installation instructions. You'll need an internet connection for this installer to fetch all the needed files. But once you're done, you can click continue. And now we're done, right? Not quite. What we downloaded and installed was a program that will download and install the packages we need. Sounds like a roundabout process, but this way we download only the things we need and not a big set of packages full of things that we don't need. So anyway, we open the MinGW Installation Manager and we need to install two things: MinGW 32 base and MinGW32 GCC G++. Those are what we need for our GCC compiler. So this is gonna be, there's gonna be a little menu on the left side of the window. Go to basic setup and you will see those two things. What you can do is either click on the checkboxes on the side or right click them. You'll see an option, mark for installation. If they're not installed, this will be the only option you can select. Mark both of those for installation, MinGW32 base and MinGW32 GCC G++. You'll see little arrows on the side, and that means those packages are ready for installation. Go to installation, click apply changes. You'll see a little window that says okay to proceed. Click apply. Once the changes are applied, you can click close. And now we need to install pthreads. It's a similar process, but instead we need to go under all packages. All packages, MinGW, and then you're gonna need to do a bit of scrolling because there isn't really a search function here. But everything is sorted in alphabetical order, so what you need to look for is MinGW32 lib pthread gc. There are two packages with the same name. What we want is the one that's labeled as dev. That's a development tool. So we mark that for installation, and then we go through the same install process as we had before. Go to installation, you'll apply changes, okay to proceed, apply, close when you're done, and then MinGW32-libpthread gc will be installed. Oh, also keep note, there is another one, but there's another package with the same name, and it is DLL. If that isn't installed, you'll need to install that as well. We're almost done. So, the last thing you'll need to do is to edit your path variable. So, this is for a Windows machine. As I said, go to your start menu and search edit the system environment variables. Click on the very first result that pops up, and then you'll have this window pop up. There is a button towards the bottom of that window, environment variables. Click that. You'll see two sets of variables. One is the path under, say, user variables for whatever your username is on your Windows machine. Click on the path variable, then click edit. You'll see a list of basically entries for the entire path variable. Click new. And remember that path where we had that MinGW installation directory? Well, if you have written that down somewhere, you're gonna need to type that back in. You type it in here, but follow it up with \bin. And that's it. We click OK, and then we click OK again, and then we click OK again. One way to make sure that we have this installed is to open up PowerShell and type in, well, there are several ways to see whether this works. You can just type in GCC by itself, and if it says fatal error, no input files, it works. But it never got any files, but it still works. If it says something like GCC is not a recognized command, then that means something is wrong. Something went wrong with the installation process. You might have to go back through the instructions to figure out what went wrong. You can also test it out by typing in GCC and then -version. Okay, we got the compiler to work. How about the pthreads? Well, to test whether this program will compile C programs that use pthreads, for us to know whether that works, we need to write a test program for us. I went through the Hello World program already from about last week, so I'd like to go through an example program that uses pthreads. It's the pi estimation program. This corresponds to section 4.4 of the textbook, and it is all about critical sections. We're gonna write the pi estimation program that we had using OpenMP, but we're gonna write it using pthreads instead. We're gonna get the same program out of it. It's just written using a different library. It's written using a different multi-threading library. So what OpenMP was, well, it was a library, but it was also a set of compiler directives used to write parallel programs in ways that are easier than, say, pthreads. Why are we looking at pthreads when we have OpenMP? Because there are many ways of doing the same thing. And I'd like to show you the different ways we can achieve the same thing with different libraries. Also, you might have access to one thing and not the other. So, let's use a formula. Well, technically this isn't a formula, it's an infinite sum. But we're gonna use this sum to demonstrate parallelism and the need for a critical section. We can start with the following serial code under the assumptions that sum is a shared variable. The number of terms n can be evenly divided by our thread count, and all the terms being added for I being an even number are positive, and all the terms for odd I are negative. So, what this is here is the pi approximation program. No parallelism at all. You can try this out. It's about 20 lines of code. You don't need anything special for this program. Just type it out using whatever IDE you like, compile it, run it, see what results you get. You can also test it out for different sizes of n to see what approximations you get. Because the next step, we're gonna need this program. We're gonna parallelize it. So, here's what it looks like when we parallelize that same program using pthreads. We begin with a few global variables. One is n, that is the number of terms in our sum. Another one is thread count, that's, well, the thread count. And another one is the sum. We also have a function prototype called thread sum. That is where our summation is happening. So see this for loop? In our pthreads equivalent program, that for loop lives inside the thread sum function. Here we have the main function. It is about 30 lines of code. We have quite a couple of things needed here. We need to get the number of threads as a command line argument. We need to allocate memory for our thread handles. We fork our threads, and then we join our threads. And then, hopefully, once all that work is done, we can calculate the number pi by... You know how the sum works? We add 1. We have the number 1. We subtract 1/3, add 1/5, subtract 1/7, add 1/9, subtract 1/11, and we do that for however many terms we have. At the end, we will have 1/4 the value of pi, actually. So, however many terms we decide to add here, we need to multiply that by 4, and then we get our number pi. So, this PowerPoint is also on Canvas as well. You can't really copy paste the code because this is a screenshot of the code. So, you're gonna have to type it out. Do your best to type it out. The last part of the code is the thread sum function. So there's quite a few parts here. Because this is a for loop that is going to be running on... This is a for loop whose for loop iterations are going to be run on multiple threads. So one way to think about it is if a serial for loop had to do every loop iteration, it would just start at the start and end at the end. But if we divided that for loop between the work of the for loop between two threads, you'd have one thread start at the start and end at the middle, and then the other thread would start at the middle and end at the end. But we can generalize that to, say, 3 threads. One thread starts at the start and ends at the 1/3 point. Another thread starts at the 1/3 point and ends at the 2/3 point. And one more thread starts at the 2/3 point and ends at the end. But we can generalize this to any end. So instead of thirds or fourths or fifths, we can divide the work as evenly as possible by any number of portions, each portion being 1/n of the work of the for loop. So that's why we need to calculate my first I, my last I, and then my n. We also need to calculate this. Because we are adding terms that alternate between positive and negative, you also need to know how. No, you also need to know what starting term we have. Is it going to be positive or is it going to be negative? And with all that information, we can set up our for loop like this. For I equals my first I is less than my last I plus plus, and then we're not done here. See this comma? We have factor become negative factor. And then we have sum plus equals factor divided by 2 times I plus 1. And that is our for loop. And that for loop is part of our thread sum function. This function is going to be called by every thread in our program. They are going to increment this sum by some number. And at the end, we're going to get an approximation of pi. So it's probably better if I actually demonstrate the program for you. So let me pause the recording so I can set up Visual Studio. Alright, we have the program as it was written in the PowerPoint presentation. Exactly as it was. If you are to use the local Windows debugger, even if you have pthreads and the GCC compiler installed, the compiler will be all like, I cannot find pthreads. So we're gonna have to fall back on using the Linux compile commands. So what we do is right click onto solution here. You need to have the Solution Explorer window open here. Right click, select Open in File Explorer. And then an entire File Explorer window will open up. What we want to do is go to not debug, but rather, we want to go to the other folder that is within this folder. So in our case, since I named the project CSE-5250 PyThreads, I have another directory that has the same name. So if I open that directory, there is my source code. There's my code. So what I need to do is type in PowerShell in the address bar. Press enter. And now I have PowerShell opened at the exact location that I have PowerShell, and it's currently at this directory here. If I type in ls, we should see our CPP file. I thought we were compiling these things in C. If you use CPP instead, it should be okay. Because as long as all the code in there is C, then the compiler will have no problem reading it as a CPP file. So what's our command? Well, if I expand this a little bit. So our command is this: gcc -g -wall -o, the name of our executable that we want, and then the name of our source code file, which is CSE-5250 pythreads.cpp, and then -lpthread. I have this set up so it gives me a different file name from the source code file, but for consistency's sake, I'll just have the name of the executable and the name of the source code file be the same, except for the file extension. So I press that, and now we have it compiled. If I type in ls, we see an executable with the same name as our source code file. So all we gotta do is type in ./CSE-5250 pythreads.exe. But this is a program that requires command line arguments, so I'm gonna give it, say, 10 threads. And it works. We got 3.14 something something. Let me zoom in here. We got 3.14 something something, and that is not the value of pi, but it is the value of pi approximated to 2 decimal places. So it works. But if we use more terms, of course, we can get an even better approximation. So if I run this a whole bunch of times, you'll notice that the sum is changing a little bit. So 3.14 something 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 691, and then 247 135. What's going on? Well, it turns out this program was intentionally written with an error, and that error is this. This increment function. If one thread is in the middle of adding to the sum another value, but another sum needed access to that same value, and needed access to the same sum, it might get the value before that first thread was even done with it. So it might get the wrong result. So now we have what's called a race condition. So this program has an error in it, and the program will end up generating the incorrect value of pi. but you wouldn't be able to tell because that error only appears in the last several decimal places here. So, the textbook emphasizes that these race conditions are not only important to fix, but sometimes they are insidiously hard to fix. The textbook uses the term Heisenbug to refer to software errors that, if you were to try to observe them, just the act of observing them somehow magically fixes the problem. But the textbook has two ways of fixing this. One makes the program even worse. Let's go through that. This is under... Okay, this is under... this is part of the PowerPoint slide chapter 4C, and this is all about section 4.5, busy waiting. Let's check that out. So our pi estimation program has a race condition. Can we fix it? Yes, we can. So the problem comes about when two threads are accessing the same value, and one thread was in the middle of updating that value, and the other thread gets the value before the other thread updates the value. So if you have, say for example, two threads that have to access a value, and it's a 31. One thread is going to do 31 plus 1 and store it in here. But at the same time, another thread wants to add 3 to it. But this thread hasn't finished updating that value, so it's not going to be 32 plus 1. It's still going to be 30. It's not going to be 32 as we think it would be, because this thread fetched this value before this thread was able to update it. So this thread thread 1, got a 31 when it was supposed to be a 32, but thread 0 was still in the middle of updating it. So it got the wrong value. So when thread 1 does its addition operation, it does 31 plus 3, and we now have 34 when we were supposed to have a 35. The concept behind fixing this is simple. If one thread is using this number, we block access to it to all other threads until that thread is done with it. One thread has exclusive access to a shared memory region for as long as that thread needs it. Here's one way to do that. So if we have this example, this is an example of a race condition where it is conceptually similar to this example here, where one thread tries to increment a value that another thread hasn't finished incrementing yet. So this example was also in the previous slide. I just didn't show it. If a thread had calculated x plus y, but was in the middle of writing its result to x as another thread began to calculate x plus y, we would have a race condition and the value of x will be incorrect. To fix this, we add 2 additional lines of code. Before that increment operation, we have while flag does not equal my rank. And then, after that, we have flag plus plus. So this flag is a shared variable. It's an integer value that is set to 0 by, say, the main thread. Suppose we have 2 threads, thread 0 and thread 1, and thread 1 finishes before thread 0. What happens when thread 1 reaches line 2? Well, notice that this is a while loop, but there's no body of the thread. There is no code to loop. So it's going to do this check here. Flag does not equal my rank. If that statement evaluates to true, it's going to perform whatever code is in the loop, but there is no code in the loop. So it just does the check again, and again, and again, and again, and again, and again, and again. We caught the thing in an infinite loop. Or at least it sounds like it. It sounds like we have thread 1 caught in an infinite loop. The only reason why thread 1 is in this loop is simply because thread 1 has a thread ID that is 1, but the rank is but the flag is 0. So with the flag 0 and the thread's rank being 1, 0 does not equal 1. This expression evaluates to true. So thread 1 does this check again because it has no choice but to do so. Meanwhile, thread 2 has its rank be 0. What happens? Well, here's what happens. Thread 0 has a rank of 0, but the flag is 0. 0 does not equal 0, evaluates to false. So it doesn't end up doing this check over and over again. So now it's free to increment x by y, and then it increments the flag variable by 1. When thread 0 increments the flag by 1, what happens is this. Thread 1 has a rank of 1, but now the flag is also 1. 1 does not equal 1 is false. So it breaks out of the loop, it does this increment option, and then it increments the flag again. We have, by the actions of another thread, we have broken out one thread out of its loop. There are a few things to consider if you're to do a busy loop. A busy waiting, as it's called. And it's this. Did you know that the compiler can do optimizations? So, the compiler, for example, will read this code and decide for itself, hey, looks like you're doing an addition operation. I'm gonna do that first before we enter the while loop. No, don't, computer, no, bad computer. The problem is the compiler only sees code as it would run on a single thread. It doesn't know the existence of other threads, and it doesn't know that X and flag are modified by more than one threads. So if you wanted to do a busy waiting, you might need to turn off compiler optimizations. So that's one consideration. One other thing that could happen is this. So in our example, thread 1 finishes before thread 2, but then it gets stuck in the busy waiting. So now it's up to thread 0 to free thread 1, effectively. What happens if thread 0 gets delayed? well, it means that thread 1 will be delayed even more. So this kind of busy waiting is known as a spin lock. And when you have situations like one of the threads being delaying another thread, this could be disastrous for performance. So what I'm going to do next is I'm actually going to demonstrate the busy waiting program. So I have the code for that as well. And let me just pull that up. Yeah, I rewrote all this code beforehand for the sake of demonstration, but I would encourage you to follow along by writing out the programs yourself and then modifying the code as needed. But don't overwrite the same code that you had before. You're gonna want to keep copies of the same code. So, what are the changes here from our old code? I do have the old code here for comparison, so well, really there isn't many changes to the code. In terms of what we have before the main function, the only change is we have a flag variable, but it's a global variable. Everything else is unchanged except for the for loop in our thread sum function over here. We introduce a busy wait before this increment option, and then after that we increment the flag by 1. However, we need to make sure that if we keep incrementing and incrementing the flag, then we're gonna reach a point where the flag exceeds the number of threads, and at that point no thread will be able to proceed from the busy wait. So to keep that from happening, what we do is increment the flag variable, and then if it ever equals the thread count, we roll it back to 0. That's modular arithmetic. And we use the modulus operation for that. So flag equals flag plus 1, and then mod thread count. So that's it. Those are all the changes we need to do. If we go to, if we open up our project in File Explorer, we go to our PyThreads program again, and then I open up PowerShell, although I have it open up right here already. Let me just close that so I can demo doing it again. PowerShell. So I have this program with changes, and now I want to compile it. If I press the up key a bunch of times, I'll see the compile command again. Let's try it with, well, what we're going to be doing is this program is going to add 10 million terms, but our previous program here only had 1,000 terms. So let's start with the 1,000 first. So this program with the spin lock, I should say the busy waiting. This program with the busy waiting, we're gonna have it add 1,000 terms. So I'm gonna compile the program. It worked, I think. Okay, it worked. And then I run the program again by doing /CSE-5250 pythreads.exe space the number 10 because I want 10 threads. It works. But I want to demonstrate something. If I make this 1 million threads by typing 1E6, that's shorthand for 10 to the 6th power. If I save that, recompile the program, and run it, it didn't take all that much time. But if I ran it with, say, 10 million threads, what happens? It starts to slow down. So I'm going to do a test, and I'm going to run it with only one thread. What gives? It was faster with one thread, but slower with 10 threads. And if I tried 100 threads, I had to stop the program because it was eating up CPU resources and it was slowing down OBS. But maybe we can get an idea of how disastrous this program is with multiple threads. Let's try a more modest 25 threads. But I want to stop it because I don't want to crash the entire. I don't want to crash my computer in the middle of recording. So you can see every CPU core on my computer, every thread, but in the other sense, I'll just say it processor. Every processor on my computer overloaded. But that's because they were all caught in that infinite loop, except for maybe one that was the one that was allowed in the critical section. So if I did it again with, say, 2 threads, it runs faster. If I say 5 threads, it runs a little slower, but we still get an answer. If I did, say, 10 threads, it runs a little more slower, but we still get an answer. But I am not going to do it with 100 threads again. So it gives. Why is it that we have a program that runs worse when we add more threads? It's the nature of our busy waiting. So, it's the nature of our busy waiting. What's happening is this. Our program is doing work. It's doing work. It's doing this. Check here. But it's not useful work. We wanted to do this, not this. But because we have it so that we have our program so that each thread does this while it's waiting for this. So it's by doing this while it's waiting for this, it's eating up CPU cycles and decreasing performance of our program. This thing sucks. But can we do anything about that? Well, we can. What we gotta do is find a way to have it so that if our program were to wait for the critical section to open up, we don't have it do something like this. We instead have the program basically have threads wait, but they don't waste resources doing so. So that's the point of our next PowerPoint slide. Slideshow again. Ever been bored, so bored that you were to say play with the little door stopper spring on, say, a door or a wall, and it would go sproing? Yeah. Our threads that were in a busy wait were basically playing with a door stopper, but to play with the door stopper was basically, in a way, one way to think about it is all the threads are waiting for another thread to finish up, but playing with the door stopper is considered a waste of company time. So we need something else. What we need is something that pthreads already has. It's called a mutex. So you can think of a mutex as a type of lock. Say you go to the gym on campus, or you just go to a gym. You want to use a locker. You have a lock. But wait, you forgot your lock. So let's say the gym has locks of its own. You pick one up from the counter, you go to your locker, you throw your stuff in the locker, you put the lock on the locker. So now no one can use it except for you. When you're done with the locker, you unlock the lock, take your stuff out, return the lock at the counter, and now someone else can use that locker. That is the principle behind a mutex. So we need a way of creating one of these things. And we have a function called pthread mutex init. This is a function that needs to be passed in two things. A pointer to a mutex, and then the second argument can be left as null. You also have this one-line option of creating a mutex, but however we create a mutex, we need to destroy it when we're done. So this is the destroy function. Pthread mutex destroy. We just give it the pointer to the mutex. So we use a mutex in conjunction with two functions, generally called lock and unlock, but in pthreads it's called pthread mutex lock and pthread mutex unlock. It's like that lock I was talking about when I was talking about the example of going to a gym and you had to borrow a lock from the counter. You get the lock from the counter, you lock the lock on your locker. When you're done, you unlock the lock, take your stuff out, return the lock to the counter. Okay, but let's say this gym has some extreme budget cuts, and there's only one locker, and there's only one lock. You can say that this is not a very popular gym, and with good reason, because this is going to be a gym that only has, say, a few people at a time. Maybe 2 or 3 people at a time. Or maybe it's a personal gym. But anyway, let's roll with the example of there being one locker, one lock. Our locker represents our critical section. Our lock represents our mutex. Someone grabs the lock, throws their stuff in the locker, locks the locker, no one can use it. Someone else wants to use the locker, there's no locks to get. So that other person has to wait for the first person to unlock their locker, return the lock, take out all their stuff from the locker, so that second person can then use the locker. In operating systems, you'll see stuff like this. But this is something that's talked about in operating systems, say CSE-4610, where you have shared resources that can only be used by one thread at a time. But sometimes you need to keep track of multiple of the same resources. That's what, if we have multiples of the same resources, but we need a way of keeping track of how much is available, you need more than a mutex. You need a semaphore. We're not going to get into semaphores, but if you're to read the section following mutexes in the textbook, that we are in section 4.6, and that is all about mutexes. 4.7 is all about semaphores. I don't want to get into that because it's basically review from operating systems. But if you want a real life example of a semaphore, if any of you have ever been to Las Vegas and you saw one of those fancy parking garages that tells you how many parking spaces are available, that is a semaphore. And then you drive inside and you see the indicator lights inside that are green or red depending on whether a car is parked there or not. Those are your mutexes. So yeah, live updates on how many parking spaces are available in a parking garage, and you put that on a light up sign right inside the parking garage. That is a real life example of a semaphore. Anyway, let's go back to mutexes. So, how it's done in pthreads is we create a mutex, and then each thread will, in this order, lock and unlock that mutex. And then once all the threads are done, once the program is finished running, we destroy the mutex. I have the same pi estimation program as before, but now we are changing it once again to use a mutex. So here's what the code looks like. We have our mutex that we just call mutex. I guess it's not really a pointer anymore, but I guess this comment is wrong. So we just call it our lock. It's a lock. In our main function, we initialize our lock by passing in the address of our mutex as our first argument, but then we pass in null in the second argument because we don't really need that second argument. Oh yeah, did I mention that this mutex is a shared variable? Anyway, we create our mutex right before we fork our threads. And then we join our threads, and then right before we end our program, we destroy the lock because we don't need it anymore. So we pass in the address of mutex. In our thread sum function, we have our lock and unlock functions. So this thread sum function is the same as it was several times before, but here is the change. Before our critical section, we have pthread mutex lock, and we pass it the address of mutex. And then we enter our critical section, and then after that, we unlock our mutex. Pthread mutex unlock, and we pass it the address of mutex. And that's it. So, once again, I have the code for this pre-made for the purposes of the video, and I'm going to copy paste that into Visual Studio. So this is the one when we're busy waiting. We have seen for ourselves that it's not the best thing we should do. Okay, so now we would go in open folder in File Explorer. We go to our PyThreads folder, and then we want to recompile our program because we just changed the source code again. I'm going to close that, and open up PowerShell again, so we have a fresh new PowerShell. Open that up. I can press the up key a bunch of times so I can get back our compile command. So it's gcc-g-wall-o, the name of our executable, the name of our source code file, -lp thread. Press that again, and we got an error. Okay, so I think I know why that is. I think I missed a curly bracket somewhere. Okay, let's try it again. Okay, there we go. That fixed it. And now we run the program again. Let's run it with, say, 10 threads. Okay, it worked. Okay, but now let's do it with 100 threads with busy waiting, and this is also with 10 million terms being added. So from before, we showed that busy waiting had disastrous performance. Will this mutex be any better? If I did it with 100 threads, it worked in just like a second or two. You saw that, right? So, with busy waiting, our threads were doing work, but that work was not useful work. Here, our threads are just... What happens when a thread were to acquire a lock, but it's already in use? Well, it's just gonna wait, but it's not gonna waste system resources anymore. It's just gonna sit down and wait. So now, if a thread is in a critical section, and another thread needs access to that critical section, it's just gonna wait. It's not gonna do the busy waiting anymore and waste CPU resources. Instead, it's just gonna wait idly until the critical section is available, so then the next thread can get the lock and enter the critical section. So yeah, this is the main thing I wanted to show you for pthreads. Really, it's just another way of creating parallel programs, but with several considerations on how we want to control access to critical sections. There are way more considerations than I want to get into, but a lot of it, as I said, was basically review from operating systems. Maybe I will summarize what all of this is, but if I am to assign you homework on pthreads, it's going to be try this program and get an execution time, or at least observe the execution time. Because if we're not careful, we can make a parallel program that runs worse than if it were a serial program. So that's one of the concerns that is in here regarding how we control access to critical sections. Sounds like OpenMP was a lot more convenient, and I can understand how it can be. But even OpenMP has its own considerations. You need to consider setting certain variables as private and others as shared. Oh, by the way, you may have noticed that I asked in an announcement, hey, would you like an extension on your first homework? And I got many responses saying, yes, please. And so you'll notice that I've done just that. So the homework that was to be due today is now due next Friday. Also, you'll be noticing that this video is a little bit later. It's coming out a bit later than I have it usually. That's because I just had so much stuff to do regarding other classes, but now we're trying to get back on track, and it means this video is coming out one day late, but it also means that this video is also jammed packed with all sorts of content regarding what to do with pthreads. We're really looking at parallel programming as it pertains to us trying to speed up a for loop. At least that's what we're going to be doing in this class. There are way more things we can do, by the way, but let's just focus on how we can use parallel programming to speed up a for loop. We can't speed up all for loops though, as we saw in OpenMP. So there are certain forms of for loops that we can't parallelize. I guess there are certain types of loops that we can't parallelize. If a loop has a loop carry dependency, we cannot parallelize it, no matter how hard we try. Sometimes there is a loop that has a loop carry dependency, and OpenMP will happily parallelize it if you told it to. I think next week I'm gonna get into the details of what you'll be doing for your midterm project. But if I do assign homework on pthreads, it's going to be you trying out a program in pthreads and then comparing performance between busy waiting and using a mutex. And it's a good thing too, because the midterm project will have you not only write a parallel program, but benchmark it, see how fast it runs. The condition is this: compare the performance of the program on your own machine. We're not comparing each other's machines. We're comparing it to our own machine because we want to isolate two variables. How many for loop iterations are there, and how many threads are there? So those are two variables. By running it on multiple different machines, we introduce way too many variables, and we want to isolate the variables. So I'll get into more details about that sometime next week, hopefully. If you have any questions about your homework, you're welcome to email me, or I never said this explicitly, but you also have the option of setting up a Zoom meeting with me. It just has to be by appointment. That's all. Right. Try this program out for yourself, and we'll come back next week and talk about a little bit about what your midterm program is going to be about. Maybe I will also talk briefly about semaphores as well, but we'll see. This is the main thing I want to get to next week, is your midterm project, because we're almost at week 8. Week 8 is the tentative due date for your midterm project, but I might just make it due on week 9 instead. But anyway, try this out. Try this program out for yourself. See how long it takes to run the program with busy waiting and with the mutex. And we'll come back next week and pick up from there. Alright, thank you. See you next week.